Developing safe, reliable and appealing products is an enormous challenge. Structural testing, FE correlation, experimental modal analysis, operating deflection shape analysis and NVH optimization are critical processes for product design, development and manufacture. In a fiercely competitive world, vibration measurement can be a powerful and sophisticated tool to create a winning product. Discover the advantages of 3D scanning laser vibrometry and learn how vibration measurement is done quickly and effectively with superior technology from Polytech. Laser vibrometry uses the Doppler effect for non-contact optical vibration measurement. The effect describes how the frequency of light is changed slightly when the light is scattered from a moving object. Within a Polytech vibrometer, a high-precision interferometer detects the minute frequency shifts of the backscattered laser light. To achieve this, the interferometer splits the light into two parts. The so-called reference beam propagates directly to the photodetector, while the measurement beam is incident on the test object, where the light is scattered by the moving surface. Depending on the velocity and displacement, the backscattered light is changed in frequency and phase. The characteristics of the motion are completely contained in the backscattered light. The superposition of this light with the reference beam creates a modulated detector output signal, revealing the Doppler shift in frequency. Signal processing and analysis provides the vibrational velocity and displacement of the test object. Vibratory motion is properly characterized as a true 3D phenomena. A complete measurement using Polytech's 3D scanning vibrometer includes the spatial nature of the motion. Vibration measurements help unravel the critical system dynamics of a test object. The 3D scanning laser vibrometer uses light as the sensor, eliminating the influence of a traditional contact transducer on the test object motion. By using scanning mirrors, the light is sequentially placed on a grid of points, measuring the motion of a complete surface. 3 measurement heads sample each grid point in 3 separate directions, uniquely determining the vector motion at that point. Vibrometers deliver meaningful results. Real-time data help to visualize the temporal signature, and frequency spectra display the characteristic resonances. For full field measurements, spatial deflection shapes are visualized as an animated pseudo-color representation, or as a dynamic 3D graphic for a better understanding of the overall system response. Making a vibration measurement with Polytech's outstanding PSV 3D scanning vibrometer is very easy. By following a simple sequence of steps, data for deflection shapes, modal analysis and frequency response functions can be taken quickly and precisely. In fact, in the next few minutes, I will set up the PSV 3D scanning vibrometer, measure a test structure and analyze the measurement data. The PSV 3D scanning vibrometer consists of 3 measurement heads and the data acquisition and management system. First, the 3 measurement heads are positioned in front of the test structure, which in our case is an aerospace compressor blisk. Each of the 3 scanning heads measures the vibration at the same measurement point along a different direction. This configuration allows the X, Y and Z components of the vibration vector to be determined at each measurement point. Typically, the measurement heads are positioned at the corners of an equilateral triangle. In a proper setup, the triangle's surface normal coincides with the average surface normal of the measurement area. After mounting and cabling the heads, the power is turned on. An internal video camera provides images of the object under test as seen from the measurement heads. These images simplify construction of measurement geometries and provide for an intuitive animated visualization of the measurement results. Before the measurement can begin, a simple two-step process is used to determine and align the angle coordinates of the scanner mirrors with the camera image and the coordinates of the measurement heads with the absolute coordinates of the measurement object. In the first step, the software helps the user aligning the three laser beams to the object under test. Thus, the cursor position on the screen image of the structure corresponds accurately to the location of the laser spots on the actual test structure. In the second step, the absolute position and orientation of the sensor heads is made known to the system. The measurement geometry can either be imported from CAD or FE packages or interactively defined with an easy-to-use graphic interface similar to a drawing program. After the interactive geometry definition, the integrated geometry scan unit obtains absolute 3D coordinates for the measurement grid. To assure the best signal quality, the PSV software uses a sophisticated autofocus function to maximize the amount of backscattered light collected. The PSV 3D is flexible in defining measurement types and associated parameters for data acquisition and sample excitation. Sophisticated algorithms are implemented for getting the best data quality out of the measurement. Various waveforms are provided to excite the object under test. In this case, they drive an electrodynamic shaker. After aligning the system, defining the scan points, and acquiring the structure's geometry, the three laser beams intersect exactly at the points of the measurement grid. Now we are ready to acquire the X, Y and Z components of the vibration vector at each individual scan point. During the measurement, the beams are scanned synchronously across the surface of the measurement object, simultaneously acquiring the three components of the vibration vector at each scan point. The measurement time depends on the settings for frequency resolution, number of averages, and of course, on the number of scan points. In any case, complex objects can be characterized with several hundred to several thousand individual measurement points in a very short time, especially when compared to traditional contact transducer methods. During the scan, time traces and frequency spectra are displayed for all vibrometer heads and also for external reference signals. Depending on the measurement type, time domain or spectral data is acquired for each sample point and can be animated temporally or as a phase-synchronous deflection shape. In the case of frequency domain measurements, the PSV software displays the averaged power spectrum after completing the scan. The user selects frequencies of interest from this or any number of individual scan point spectra. The system calculates the corresponding operational deflection shapes. The cursor mode allows the display of data at the specified frequency on the geometry of the object by simply mouse-clicking points on the spectrum. The results may be shown in many different formats. The Polytech signal processor is the user interface to the math library included in the PSV software. Designed as an easy-to-use spreadsheet, measurement data from different sources can be post-processed by simple drag-and-drop operations. If you want to further analyze measurement data you have already acquired, you can recalculate it and present the results in a direct comparison with the original data. For this purpose, you can transfer the data to the signal processor and then process it further. You can save the data calculated this way with the measurement file and display it again at any time. Any screen display can be saved to a range of standard graphic formats, and animations can be saved in standard movie format, AVI, for replay on any computer. Measurement data can be provided for post-processing in modal analysis, CAE and FEM correlation, sound field prediction and power flow software packages using export filters for universal file format, MeScope, MATLAB and ASCII. In summary, the PSV 3D is an exciting new tool for making critical vibration measurements that significantly improve the design, development and manufacturing of automotive, aerospace, military and consumer product. It increases accuracy by eliminating mass loading, decreases measurement time by shortening setup, improves deflection shape analysis with thousands of measurement points and offers complete vibration vector components for the best in modal testing and FEM correlation. Polytech can make this technology available for your application through a variety of programs. Check with your local office to find out about direct purchase, lease, short-term rentals and measurement services. Polytech. Advancing measurements by light.